Okay, it looks like the people that are rolling in has finally settled down. So we can get started. Well, yeah, so hello everybody. Thanks again for taking your time to join our webinar today. The objective of the webinar is to go over the workflow for collecting the and processing the L1 and P1 data based on our experience with the system so far. So just one housekeeping item. If you have any questions or comments, please put them in the chat below within this webinar session. We'll be recording the session, so we'll send it out to people that have missed out on this. So before we jump into it, I'd like to introduce the team. So my name is Van. I am the marketing manager here at Candrone, and over the past 2 years, I've been flying LiDAR and doing training and flight reviews at Candrone. Today, I'm hoping to share some insights into LiDAR drone operations based on this experience. And now I'll pass it to Tom to introduce himself.
Thanks very much, Ben. And hey, everyone, wherever you're from in the world, hope you're having a great day and welcome. I'm Tom, and I'm the survey technologist here at Candrone. I've got 10 years of experience in the surveying industry across New Zealand, Australia, and Canada. And I'm pretty passionate about integrating new technology in surveying and other related spatial sectors. I'm really keen to explore what this new equipment's capable of. And yeah, that's enough about me. So I'm going to pass you on to Russell.
Thanks, Tom. I'm Russell Snow. I'm Candrone's sales manager. We have a team of 5 with staff based here in BC and in Ontario. We handle inquiries from across North America and often beyond. We also have a rentals and services team of 4, and I'll talk a bit about that side of the business later. So why should you choose Candrone? Okay. Candrone is Canada's leading robotics consultancy and a one-stop shop for everything related to airborne scanning and mapping. We've been in operation since 2009, and we're a full-service drone and LiDAR agency offering everything from hardware and software sales through to rentals, training, and piloting services. We have tens of thousands of happy customers and have inspected upwards of 8,000 wind turbines, amongst our many achievements. And we've been working with LiDAR since 2015 and have an expert knowledge of many industries, including surveying, construction, forestry, mining, search and rescue. And we also have considerable experience of building drones and creating custom engineering solutions for our customers. Last but not least, our technical team are not only hardware and software experts, but they also manage the rental and service side of our business. In short, you're in safe hands. And speaking of safe hands, I'll hand back to Van to run through today's agenda.
All right, so the webinar will consist of just the initial part will be going over some system overview and specifications of the M300, P1, and L1. And then finally, in the last sections, we'll be going over the workflow for the L1 LiDAR and the P1 photogrammetry camera. And at the very end of it, we'll be finishing up with some Q&A. So without further ado, let's get started.
Thanks, Van. Now, I'm sure most of you are familiar already with DJI's flagship enterprise platform, the Matrice 300. So we're not going to spend too much time talking about the drone itself today. Suffice to say that if you want to fly the P1 or the L1, then you're going to need one of these. Prices start from a little over $13,300, which includes the drone, the controller, charging station, 2 batteries, and a hard case for both the drone and the battery station. Now, there are a few key payloads that are on the screen now, and you have the H20, H20T thermal cameras, same with the X2 and XTS and Z30 zoom camera. But the reason we're here today is to talk about the P1 and the L1. So the M300 can fly up to 3 payloads at once and carry up to 2.7 kilos. But most pertinent for today is that the L1 and P1 can only be flown in the single downward gimbal mode. So one to bear in mind. So with that, you're going to be flying a single gimbal. On the screen, you can kind of see what the flight endurance looks like. So with no payload, you're going to get around 55 minutes. Sliding scale down to around 31 minutes if you are maxing out your payload. From experience, we have tried and tested and see the P1 and the L1. You're going to get around 40 minutes. There's obviously some environmental factors like wind or battery performance that could influence this. But on the whole, that is where you are looking. So we're going to start today with the P1. The P1, the reason many of you are here, it is a 45 megapixel full frame sensor with a mechanical shutter, and it is DJI's Survey Beast. So doubling the resolution of the P4 RTK. And we talk about survey grade accuracy, and it's a term that people use without really diving too much into. So I'm going to hand over to Tom, and he's going to talk a little bit more about what we mean by survey grade.
All right, thanks very much for that, Russell. Yeah, as you mentioned, survey grade is something that gets bandied around a little bit in some of the marketing spills for equipment that's out there. Now, obviously, when it comes to any of this equipment, good survey practice is always a prerequisite of getting survey grade accuracy out of any of this equipment. And you've got to also be thinking globally about all of the positioning elements in your survey or in your network. So in the context of the P1, by survey grade, we really mean we're talking about the hardware that's been specifically designed for the survey industry. You know, the fact that it's one of the first full frame interchangeable lens cameras to be made by DJI that integrates with DJI's system, and you know that it matches with the M300 platform, which has got dual RTK sensors and has the ability to tag RTK locations to all the photos. So the P1 and M300 isn't the only DJI system that has RTK capability. Some of you may have experience with the Phantom 4 RTK and maybe wondering, what's the difference? Why would I be looking at or be interested in the P1? Really, it comes down to software option differences, color accuracy, speed, and versatility. As you can see in these images here, you can still get the same resolution, you can get the same GSD out of Phantom 4 RTK, but you've got to fly a lot lower and probably a bit slower. You're not going to get the same sort of color accuracy out of the photos from the Phantom 4 RTK. So it really just comes down to a question of, you know, what size sites are you going to be surveying and what kind of GSD do you need to get down to? And is it actually going to be practical, you know, to be flying the Phantom 4 RTK at the height that you need to be able to get the resolution that you want? Obviously, with the P1, you can fly a lot higher and get that same GSD. And as I mentioned before, there are other software advantages of the P1 that we're going to dive into a little bit more now. So one of the new features of the P1 and the M300 is a smart oblique capture, which is a pretty cool function in that it's essentially giving you 5 different camera angles if you select this option in your survey. As you can see in the GIF here, basically every 0.7 of a second or something like that, the gimbal flips up and takes a photo on a different angle. So what that means is you're essentially getting a lot of oblique photos, which in some bundle adjustments really adds strength to it. Not only that, but you're also getting a higher resolution or more detail on vertical features such as building facades, quarry walls, retaining walls, that kind of thing. You don't get the kind of interpolation and sort of stretching that you see quite often on photogrammetry meshes when you're just taking nadir images. So the other thing about the smart oblique capture is that it's really easy to do in DJI Pilot. It's literally just a button that you press and the flight plan changes automatically and you automatically get all those oblique photos. Well, you can do that in some other softwares and with other systems. Quite often it requires a lot more work and you don't get the same level of diversity of camera angles. So to talk a bit more about the camera itself and the sensor, I'm going to pass it over to our photography expert, Van.
Thank you, Tom. So for those who are familiar with photography, the physically larger image sensor of the P1 has more surface area for light photons to be captured by the sensor. So what this means is that you will be able to get better low light performance out of the camera, allowing you to capture data in poor lighting conditions while maintaining a relatively low ISO and a higher shutter speed, which will help reduce the noise from the data that can affect the final data output. So continuing on with that, the larger pixel size, the dynamic range also increases, giving you more details in your images, reducing blowouts from lighter surfaces and keeping more details in the darker area. This is represented below with the image comparing the P1 shot of the ground control point and the P4 RTK. And as you can see, you can get a lot more detail. The image looks crisper and the color looks more vibrant in that image comparison. So you can see all the whites aren't being blown out and providing more, that will in the end provide more tie points in your data processing. So now I'll pass it back to Russell to talk about the L1.
Thank you, Van. The L1 is DJI's first foray into LiDAR, and as you would expect, they've shaken up the market by hugely reducing the entry price point into LiDAR. The unit features the LiVox Avia sensor, which has a 70-degree field of view. It is a solid-state LiDAR. It has a 20 megapixel 1-inch sensor. Interestingly, it is the same as the one in the P4 RTK. So the L1 can actually be used as a photogrammetry camera by turning off the LiDAR and flying a photo-only mission. DJI claims accuracies of plus or minus 5 centimeters in the vertical and plus or minus 10 in horizontal. And we'll get into those accuracies a bit later in this meeting. And the other thing I want to mention is that it's IP54 rated. However, we wouldn't always recommend flying LiDAR in particularly heavy rain, given that rain will show up as noise on your scan. And the last thing I want to mention about it is that it can only run in that single gimbal mode, so you can't run it in dual or upward. And that is about it on the unit itself, and Tom is going to talk about the different scanning modes that it has.
Yeah, for sure. Thanks for that overview, Russell. Yeah, as you mentioned, we do get a lot of questions about the whether you can run the L1 with other payloads like the P1. Unfortunately, it's only can run one at a time. So a little bit of a deeper dive into a couple of the elements, I guess, in the L1 system. As Russell mentioned, the LiDAR sensor that's actually used in the L1 is called the LiVox Avia. You can look up the specifications if you're into that kind of thing for the LiVox Avia. One of the key things that I really like about the way DJI has implemented this sensor is they've given you the option to turn on to basically customize your field survey. One of the things you can do is change the scanning mode. So you can either use the non-repetitive or the repetitive line scanning. The images below sort of give you a fairly good indication of the way that the scan actually happens. The thing you got to remember is that this is not like a traditional laser scanner, which is mirror-based. There are a lot of LiDAR sensors that are mirror-based, and most terrestrial laser scanners are as well. This one's a solid-state sensor, which does have some different characteristics. When we're flying aerial topo missions, I would recommend using repetitive line scanning, as when you're flying at higher speeds, which DJI actually recommends flying at about 10 meters per second or 8 to 10 meters per second. With the non-repetitive circular scanning, especially if you're flying a bit higher, you can end up with some gaps in the data, as you can probably imagine from that GIF on the left. So I guess one thing just to mention about that is that that isn't actually something that a lot of other LiDAR sensors will actually let you do, or a lot of other LiDAR packages will let you do. Quite often it's just if they fix it on one option and that's it. So moving on to the DRTK2, I thought it would be worth just mentioning this briefly. The DRTK2 GNSS system is the DJI's version that pairs with the M300, and what we would recommend for using with the P1 and the L1 if you're looking for a really simple workflow and a low, I guess a low learning curve or low setup requirement. So the DRTK2 just communicates by normal radio connection to the M300. You can use an N-trip connection with the DRTK2 and the M300, and you can also process with PPK. Now that's something that DJI Terra does all itself. It's all just one push button. There's not really any requirement for you to have to do anything special. It's basically just drag and drop folder onto your computer and press go on DJI Terra. So the DRTK2 itself is super easy to use and connect to. It's only got 3 buttons, and all the controls are done through the DJI Pilot app. There isn't the same level of customizability as you might expect with other survey grade GNSS receivers, which can be an advantage or a disadvantage depending on what kind of business and what kind of use case you have. And obviously, because you've got an N-trip connection capability with the M300, you can use third-party bases. And you can always use them for PPK processing. There is a workflow for doing that in DJI Terra, which we aren't going to go into in this, but we can provide that later on if people are interested in it. One other thing or a couple of other things I just wanted to mention, just the quality of the DRTK2 antenna compared to other low-cost GNSS units of a similar sort of range is actually pretty impressive. Yeah, comparing it to 2 other low-cost GNSS units, I found that it tracks more satellites, more phases, and also we get I guess, less tendency to have cycle slips. As you can see in the images on the right there, the top one, the top GNSS unit there in GPS and GLONASS experienced a lot of cycle slips in the same area at the same time. The DRTK2 had considerably more coverage, and that was reflected in the post-processing results that we got. So moving on, I'm going to pass it back to Van, and he's going to tell you about the point cloud live view option, what's got him excited about it.
Thank you, Tom. So yeah, one of my favorite things about the DJI system is its integration with the smart controller. The smart controller allows you to plan, execute, and monitor everything from one device. This reduces the need to bring any extra equipment like a ground station computer into the field. And traditionally, I would be using one application for the mission planning and then another application for monitoring the LiDAR. The big advantage of the DJI L1 system is that you can plan your flight, configure the LiDAR sensor, and monitor your data all from the smart controller. The other thing that I really love is the point cloud preview, which is a great feature if you want to fly the LiDAR system manually, because it allows you to see how much overlap you've covered, and it's a great handy feature for facade scans, or if you're trying to get more details within your building scans. So continue on into the DJI workflow. I've broken it down into 5 sections. We'll go into kind of the mission planning with the DJI app, data acquisition, data processing, a quick overview of what Terra does for the L1 data, and some data analysis. So with mission planning within the DJI app, it's all completely integrated, makes everything super simple. to do. So the first thing you do is select the mapping mission, then select the area that you want to be scanning, and then you want to select the camera type. So within the DJI app, there's two options with the L1. You can do a LiDAR scan, or you can do a photogrammetry mission. So if you do choose to do a photogrammetry mission, you have to make sure that you set the appropriate overlap settings. With regards to the actual data collection, some of the parameters that we would set are the flight altitude. So DJI recommends flight altitude between 50 to 100 meters. From my experience, we've had great success flying at 80 meters. This will allow you to clear most obstacles in urban environments while providing efficient data collection by not having too much overlap requirements by flying at a lower altitude. As mentioned before, DJI recommends flying at 10 meters per second. Typically, with the other LiDAR systems that I've used in the past, you have to fly at 5 meters per second. So you can get almost double the efficiency in data collection in that sense there. As for overlap setting, generally we fly at 50% overlap. This will help provide adequate coverage in case there's some elevation change, so that you'll still be able to fill in the gaps between your flight lines. And then we use the repetitive line scan, as discussed earlier in the webinar, that gives us the best accuracies. And as of right now, DJI Pilot for LiDAR missions does not have terrain following capability. So we have seen it in the past firmware version, but it seems to have been removed at the moment. So we're hoping that they bring that back in the near future. And one final note is from what I've been noticing from people that have received the L1 system is that you need to make sure that you change the maximum flight distance within the DJI Pilot app, or else you'll run into errors if the mission length is a little bit too far from your starting point. Okay, so for data acquisition, so the first thing we do when we get on location is we set up the DRTK base station. You can set this up over a known survey point where you can manually input the base station coordinates in the advanced setting within the DRTK. Please note that when you do enter the antenna height that with your survey point to add 1.8 meters to the DRTK antenna height, and the coordinates need to be in WGS 84 ellipsoidal coordinates, and the base station needs to be within that area, or else you're going to get some errors when inputting the coordinates. So with best practices with LiDAR, you always want to get some GCPs within the survey area. One of the advantage of LiDAR systems is that you can go and collect the data before collecting the GCPs. So once you've done all that and have the DRTK all set up, turn on the aircraft, ensure that you have a fixed position with the DRTK. It's important to note that the L1 does require a 5-minute warm-up period for the IMU and the INS to warm up, and the controller will notify you once the system is ready to fly. One nice thing about the M300 is that it does have the hot swap capability. So you can save time in the field when you're doing back-to-back LiDAR missions just by swapping out one battery at a time, and that keeps the L1 LiDAR warmed up and ready to go. So once that's all ready to go, you can tap the fly icon and it will upload the mission to the aircraft. The aircraft will fly to its starting point, perform a couple back and forth maneuvers before actually starting the mission. This is completely normal, and it's the way that the system calibrates itself. And this will happen at the beginning and the end of the flight. So just talking a little bit more about the IMU calibration. So it's important to note that the calibration needs to be performed every 100 seconds of flight if you're flying in a straight line. So this works out to be about 1,000 meters if you're flying at 10 meters per second. So this is an important aspect to consider when you're planning your LiDAR missions within the DJI app. Within this image up top here, you can see that you have the mission flight lines, and it indicates the length of each flight line. So this is about 511 meters. The yellow lines on within the mission planner are areas that do not collect data, and they actually help to calibrate the IMU system. So yeah, just keep that in mind. And DJI's current firmware will only perform the calibration at the beginning and the end of the flight. So you need to plan your mission accordingly. They are, however, working on a firmware to automatically incorporate that within your flight lines if your flight lines are, let's say, over 1,000 meters. So data processing. So once you've collected all your data, all the raw data will be stored on the micro SD card that's in the L1. This includes the DRTK base station data along with the image files if you do choose to colorize the point cloud. So when you import the folder into Terra, it'll automatically be read and it'll automatically be able to process all this data. One thing to note is the default coordinate system will be in WGS84. So within Terra, you're able to select the output coordinate systems. Another note on the Terra is that it is included with the L1 and it will allow you to do some basic processing for the L1 data. However, more advanced functionalities like the point cloud optimization feature requires the Pro or electricity versions. So the point cloud optimization tool helps to improve the relative accuracy of your data by eliminating the redundant data on the edges. There's not too much information available about this feature at the moment, but the functionality is currently free for the first 6 months that you purchase the L1 system. So for data analysis, so in its current state, Terra is primarily used as a pre-processing software for the L1 in order to generate an LAS file. It only offers very basic measurement tools like for length measurements, volume, and area. So what we did was we used the LAS output from Terra in order to load it into our other point cloud viewing software in order to do things like control point accuracy assessment, denoising the data, and then to finally generate some products like digital elevation models. So now I'll pass it back to Tom to just look at some of the L1 data that we collected around here.
All right, thanks very much for that overview on the workflow, Van. Very comprehensive. So let's have a look at a data set we collected with the L1 and have a look at the parameters we used in the field and the results that we got. So the parameters we used, we basically flew a 45-acre mission in 5 to 10 minutes, set at 80 meters elevation and flying at 10 meters per second with about 500-meter long lights. Now we had 3 returns set on this particular mission, but you can select just 1 return. Now, empirically speaking, we have noticed that if you just have 1 return turned on, the point cloud spread seems to be a little bit tighter, and we're doing a bit more research into that ourselves at the moment. Obviously, if you're doing surveys with vegetation, you probably want to be having 3 returns turned on. Now, that again is a very simple to select function in DJI Pilot when you're out in the field. So as you can see here on this GIF, we've got a classified ground layer, and we've also got a RGB render using the onboard 20 megapixel camera. Now, that is a point of difference that we've noticed with the L1 is that it's a completely automated process of registering the photos to the point cloud, and it seems to be very accurate. So if you've got a need for RGB rendered point clouds, then the L1 is certainly a worthy consideration. So we process this data set completely in Terra. It's very simple, as Van showed. And then we did our QA on the data set and a bit further processing in some third-party point cloud software. So how does the data check out? So as we mentioned, Terra processes basically the raw data outputs in a very automated fashion and gives you that point cloud output that can be treated as one homogeneous data set. I'd think about it a lot like many of the other geodetic processing softwares that we have in the survey and spatial industry, where you process the raw data initially in that manufacturer's software, and then you export it to your CAD software or point cloud processing software to do the analysis and further reduction. So looking at the data set in the bottom, you can see there that we've got two cross-section views. The red one is the data set prior to doing a denoising or removing of outliers, and the green is after doing removal of outliers. So as you can see there is a bit of spread on the data sets, and this is a pretty typical thing that you'd see from most lower cost LiDAR sensors. So you might be thinking about the specification that Russell mentioned at the start, which was an RMSE of 50 mil vertically and 100 mil horizontally. Now, when you look at these data sets, depending on what the feature is that you're surveying, you can expect to actually see a wider spread in your point cloud cross sections than 50 mil vertically and 100 mil horizontally. Now, why is that, you might ask? It's due to the other specifications of these LiDAR sensors. So one of the elements that you've got to take into consideration when you're considering how to use this tool in different applications is the beam divergence. So as you can see on the left here, I've got a bit of a diagram of actually what the beam that's emitted from this solid state LiVox sensor looks like. So you're talking about a fairly long, skinny beam footprint splash on the ground. And at 50 meters height, you've got about a 0.4 of a meter beam splash long and about 0.3 of a meter wide, or 0.03 of a meter wide, or 3 centimeters wide. So what that ends up translating to in your data sets is if you're dealing with small features, you know, say curbs or like really small retaining walls or steps even, you'll end up seeing a bit of noise in that data set because the beam splash is, you know, the size that it is. You can obviously improve the beam divergence by flying closer to your subjects, and yeah, because it's an angular value, that's always going to improve it. You've also got to consider the angular accuracy of the LiVox sensor is around 45 millimeters at 50 meters. So really moving on from that, what results did we find when we compared this to our GCPs? So we classified a ground class in our third-party software and compared this ground class to our GCPs that were surveyed by a network RTK GNSS receiver. Now, the 10 GCPs that we measured, obviously using network RTK, does have its own limitations and errors. So we're dealing with probably somewhere in the region of 20 millimeters at 95% confidence horizontally and 30 meters vertically at 95% confidence. For the purpose of this survey, we really wanted to try and confirm or validate the results that DJI, or validate the accuracy claims that DJI made. And as you can see here, we've got a root mean square error of 6 centimeters and standard deviation of 4 centimeters. So all in all, it's pretty well in line with what DJI have, with what DJI's claims are. But you've got to remember, you know, there is a difference between measurements on hard flat surfaces to when you're measuring, you know, undulating or complex features. So again, there does need to be some consideration and planning around what outputs you need to get, and what your client or what your end use of this data set is. So that's enough of the L1. Now we're going to move on to the P1 workflow. So we're going to give you a bit of a run through on a sample survey we did with the P1 and give you a run through of the various elements that you've got to consider and what results we got. So mission planning is done in DJI Pilot. We'll run through that. Data acquisitions and the settings we used. We'll also be talking about data processing in DJI Terra only, and then the results that we achieved. So in terms of the mission planning execution, you're going to see a lot of similarities between the L1 and the P1. That's by design by DJI. The intent with these systems is that there's a very low learning curve to be able to become familiarized with these systems. And it's pretty simple. It's, you know, as you can see in the images there, it's all slide buttons and yeah, a very easy interface to use. Now, one thing of note is with the P1, terrain following is actually something you can do. Now, you may wonder why on the P1 and not the L1. I would suspect it's something that is very much in the imminent future for a firmware update. DJI seem to be pumping out improvements and additions to the capabilities of both of these payloads on a pretty regular basis, and I would anticipate the L1 is going to have terrain following in the near future too. On the subject of terrain following, it's a pretty easy thing to set up. While there is no default terrain model in the DJI Pilot app, you can either use the shuttle radar terrain model, which is the topography model, which is freely available and covers the entire globe. Obviously, you need to be a little bit careful when you use low resolution models like that, and you're trusting it for terrain following. I think the SRTM model is accurate to about 30 meters. You can also use any other DEM or DSM model that you may already have, whether that's a LiDAR model that's been previously picked up or a photogrammetry model. That can really easily be uploaded onto the controller, and it's literally a case of just selecting the file and it'll be uploaded. So in terms of the settings we used in the field on this particular occasion, we flew over a urban area at 120 meter height at 15 meters per second using the smart oblique mode. Now we did this really because we wanted to try and test out the efficiency of the system and its capability to pick up large areas with lots of oblique photos. So less than 10 minutes, we picked up about 15 hectares. So in terms of the data processing side of things, we're only going to talk about the DJI Terra workflow here. You can obviously run the photos from the P1 and the M300 through third-party software, but the DJI Terra does come free with the P1, and I think you get the Pro version for a few months, as Russell mentioned earlier. The DJI Terra desktop application is really simple to use. In this particular occasion, we selected high resolution, and we only used the RTK positions that were derived in the field from the drone to calculate the model. Now, obviously, if you're doing a commercial mission, this is something that you would want to include GCPs in your constraints or to constrain the bundle adjustment. But in this particular instance, we really wanted to get an idea of what the P1 and M300 combo is capable of without constraining it to GCPs. So the georeferencing RMSE that we got from the bundle adjustment in DJI Terra was about 1.8 centimeters, which correlates with the GSD size or the pixel size on the ground. So at 120 meters, we managed to get a pixel size of about 1.8 centimeters. Now, when we moved the data set to third-party software to do further analysis, we exported a 2D orthophoto and a 3D point cloud in the LAS format. Now, a couple other things to mention. You can process multiple data sets at once, and you also can select when you're creating a processing mission, you select either a 2D or a 3D processing at the very start, and that will determine whether you can get an ortho photo or a 3D point cloud out of it. So moving on to the results. How did it all look? So comparing the point cloud that we got from DJI Terra to GCPs that were surveyed with network RTK GNSS, we got a root mean square error of about 22 millimeters or 2.2 centimeters on hard surfaces. Obviously, the P1, while it's very good, it's still limited by survey of vegetation. You don't get any vegetation penetration with it, so that's a consideration if you're deciding between whether you want to go for the L1 or the P1, is how much vegetation you're going to be dealing with. So that's enough from me. Now I'm going to pass on to Russell to go through some of the finer details of DJI Terra and the options within that software.
Thank you, Tom, and thank you, Van. That was very informative. I know I learned lots there, so I'm sure that everybody else has too. Now, there are 3 versions of Terra: the free, the pro, and the electricity. The electricity is targeted at the utilities sector, and it's not something we're going to cover today. However, you do get 6 months of both pro and electricity included in both the P1 and the L1. And that's good because 6 months it can defer the cost, so you don't have to buy it all up front. However, for LiDAR, you are almost certain to need the pro version, which allows you to create 3D mission plans as well as 3D models and maps. And perhaps most importantly, you also have access to the point cloud accuracy optimization tool and the GCP analysis that Tom and Van have already mentioned. So once your 6 months expires, you need either a subscription, which costs $2,030 per year, or a perpetual license, which is $5,800. So as the guy said, Terra is what we call a pre-processing software. So it only gets you as far as georeferencing your point cloud and then exporting it, most often in LAS format. And if you then want to do any post-processing, you'd need a different software. We're not going to discuss that in this presentation, but feel free to ask us in the questions or reach out to the team after this event. And with that, we're going to do a little bit of a discussion on the different survey options that we have discussed and do a little comparison. So I'm going to kind of take it from a sales side and the inquiries that I get. And typically, when it comes to surveying, you're looking at either a photogrammetric or a LiDAR solution. If we start with P4RTK, what you've got is a drone that does one job only, but it does that job very well. It's got a relatively low price point and it delivers excellent results for that money. However, as we've seen, the resolution and the coverage can't compete with what you get with the P1. That, with the ability to change the payloads on the M300, gives you a level of versatility and an element of future-proofing that you just don't get with the P4. And now, when deciding between photogrammetry and LiDAR, one of the most often unconsidered factors is the post-processing time. LiDAR collects data in 3 dimensions, whereas photogrammetry is taking 2-dimensional data and interpolating it to give you a 3D model. This means that you need a lot more time and computer power to process photo-based data. So we typically say that you're looking at 1-to-1 for LiDAR. So 1 hour of scanning means you need 1 hour of post-processing. Whereas for photogrammetry, you're looking at probably more like 4 or 5-to-1. So that's always something to bear in mind. And then for me, LiDAR, very importantly, doesn't rely on visible light. So you aren't as constrained with regard to when you fly. Photogrammetry requires a good amount of daylight, and any kind of shadow can affect the quality of your data. In theory, you could fly LiDAR at night, although that's obviously not something we would recommend. Tom, Van, do you have anything to add in terms of kind of what you've seen operationally?
Yeah, for sure. Obviously, all of the systems are very similar in terms of the workflows in the field and in the office. It's been designed that way. But you really need to think about, I guess, two elements. What is the scale of the typical project that you want to be attacking with these systems? And what kind of level of versatility do you need? The L1 is really going to come into its own when you're dealing with vegetated sites. That's something that you're not going to be able to get any kind of, I guess, representation of the ground when you're dealing, when you're trying to do a topographical survey with the P1 or the Phantom 4 RTK. And then obviously with scale, that's something that's got to be considered if you're deciding between the photogrammetry solutions, the P1 or the Phantom 4 RTK. I guess one other thing to mention is just when you invest in the M300 system, you've got, I guess you've got the flexibility of being able to run with either the P1 or the L1, as well as the wide variety of bolt-ons that can be purchased separately from third-party manufacturers and from DJI for the M300 system. So that's basically all I've got to add. Van, what about you?
Thank you, Tom and Russell. That pretty much sums it up. Yeah, I mean, in terms of the M300 platform, you do have the flexibility of adding other cameras like the H20T or the FLIR Zenmuse cameras. So you can even do things like thermal mapping. But yeah, the M300 is just a whole nother beast. I have a lot of confidence when flying the system in the field with the 6 direction, obstacle avoidance system. Gives me more confidence when flying such an expensive payload. Other things like redundancy within the GPS system, the battery, and the IMU. Just overall adds a lot of confidence when I'm in the field with this M300 system.
Sounds great. Thank you, guys. This is the last slide before we move to questions. So we've got a few coming in. Just a reminder, if you want anything answered, please drop your question in the chat box, and we will do our best to get through all of them in the time we've got. So the question I get asked multiple times a day, when can I get my hands on one? As any of you will know, if you've actually tried to buy one, these are currently as rare as hen's teeth. Apologies if that's a UK expression, no idea. DJI is telling us that normal delivery timelines should be achieved by the end of July or beginning of August. Until then, I cannot stress enough that the only way to get your hands on one is to place an order with us. We can only order from DJI with a customer order, and we deliver the units that we do receive strictly in the order that they were paid. So yeah, reach out to us afterwards. We can give you more information. The other thing we do have is we have the M300, the P1, and the L1 available in our rental and service fleet. So if you want to inquire about how that operates, just get in touch with us, and we can either rent the systems to use yourself, or we also have pilots that can come out and fly the job as a service for you. So that's it from us. We are now going to take some questions. I think we had some come in beforehand, which we're going to start with. Is that correct, Tom?
Yeah, that's right. We've got a number of questions that have just come in. Just a reminder, if you want to ask a question, just go into the question box on the side of your screen and tap something in. So the first question we have here is it possible to upgrade the L1's accuracy to survey grade accuracy? At the moment, it is not enough for some applications or many applications. Now, that's a fair point. The L1 is definitely not a universal survey tool. You're not going to be able to use the L1 and a drone to go and replace all of your topographical survey tasks. Where LiDAR systems and aerial LiDAR systems really excel is in mapping continuous features such as power lines and doing topographical surveys of natural surface features or features that aren't really small and intricate. So really the advantage you've got there is, in the example that we gave before, we surveyed a 45-acre site in under 10 minutes. You know, we're not going to ever get the same accuracy as if you went out with a total station or a gun and, you know, surveyed those features manually. That's not, or used a terrestrial laser scanner, obviously. That's not really the intent of these systems, but what they're there to do is really provide a high efficiency topographical surveying solution. So hopefully that answers your question.
Yeah, Tom, I also wanted to add that you know, very often when people are new to LiDAR or considering it versus a photogrammetric solution, you know, you're often considering taking a few very accurate points when you're doing a traditional survey versus something like a LiDAR scan, something like the L1, where you're probably going to get anywhere up to 500 or maybe even 1,000 points per square meter. So that actually that finished result that you get, it gives you a lot higher, the perception of a higher accuracy than what you've got on the individual points.
Yeah, for sure. And I guess one other thing to mention there is that, you know, you're basically collecting passive data and then adding value by working with it later on in the office. The advantage of that is that you collect all of the data while you're out on site. There's less likelihood that you're going to have returns to site, requirements, you know, oh, we missed the back corner of that building or whatever. That's something that, you know, when you're picking up the entire site with a LiDAR sensor such as the L1, you don't have to worry about so much. As long as you've got the whole area, you've got all the data. So that's another key consideration. We've got another question here. It's, please, can you tell me how the L1 compares to the LiDAR V70? Russell, do you have an answer for that?
Yeah, obviously the two systems use the same sensor, the Livox Avia. It's slightly more expensive, but you know the results we've seen are very comparable with the L1. So the only advantage I'd say is currently that the V70 is much more widely available. You know, it's on shelf, but you know once the L1 is ready, then you know that difference will be lessened.
Right on. Okay, just cruising through, we've got questions are raining in now. Does the RGB sensor on the L1 color the point cloud using full resolution from the sensor, or does it scale it? If you flew lower, could you get decent quality color or texture detail in the point cloud? Now, I guess if I'm understanding this question right, you're asking if basically can you get a more photorealistic point cloud if you fly lower? The real limitation in the RGB colorization is really just the point cloud density. Even though each point is going to get an RGB value attached to it, even if you're getting 500 points in a square meter, that's 1 point every 5 centimeters. So really the limitation there is that you don't have that much density in your point cloud to be able to create a super photorealistic mesh if you start zooming in to a really high level. You know, obviously using the L1, you still can create textured meshes and photorealistic meshes using DJI Terra and exporting something like a OBJ file if you're looking for reality modeling applications. So we've got a question here. Have you tried doing a 120-meter AGL LiDAR flight with ground checkpoints? How does the cloud and accuracy look? Again, we haven't done a 120-meter AGL LiDAR flight. We have done a 100-meter LiDAR flight, and I guess what you end up finding when you start going a bit further out, generally the main thing is as the beam divergence gets higher, you end up getting a little bit more noise when you are dealing with complex features. So when you're like looking at say a sloped roof, or where you are looking at like edges of sharp edges of things, that's where you start getting a bit more noisy data as you start flying higher. So in terms of accuracy, we actually find if you are surveying GCPs just on flat ground surfaces, the accuracy doesn't actually change a huge amount. You're still dealing around that root mean square error of 50 mil. But yeah, you've got to consider the limit, I guess, intended use case and limitations of the sensor. Okay, moving on. Is there any way to do a geoid height above GRS 1980 ellipsoid in DJI Terra for GCPs? Similar to Pix4D process when using a local geoid such as CGVD28HT2. Now, DJI Terra is currently in the process of adding more and more geoids into DJI Terra, and at the moment, I'm not sure if CVD28HT2 is currently in there. I think CGVD 2013 is for the Canadian users here. And
yeah, sorry to add to that, Tom. I am looking in the select coordinate system within Terra. It does have a GRS 1980 ellipsoid capability. It's EPSG 4401 and then EPSG 4047. So that's what I can see at the moment.
Yeah, for sure. Thanks for that, Van. So yeah, basically the workflow for using a geoid height above the ellipsoid, that's a possibility in DJI Terra, simply put. Next question is about the L1. What would be the best setting to get good vegetation penetration and low noise? That's repeat, return, speed, height, and overlap. That's a great question. So pretty much to get good vegetation penetration, you're wanting to increase the point density on the ground. You're wanting to use use 3 returns, and having at least 50% overlap is going to increase your chance of getting points to the ground. Also, flying a bit lower is going to help out a little bit in terms of having a higher, I guess, increasing the beam return intensity. And yeah, it's also going to reduce the amount of beam divergence. So next, oh, sorry.
Yeah, so I can see the next question here is can the L1 be aimed at other angles? Yes, you can. I've made the mistake of actually while we're flying the LiDAR mission and accidentally tilting the LiDAR up a little bit, and it kind of messed up the scan. But yes, you can. You can adjust the L1 angle in order to capture like facades and buildings and different angles.
Yeah, the next question, can the pilot manually fly L1 missions? I realize it's probably not recommended. Look, I guess Van's probably the best one to talk to that.
Yep, yes, you can. Yeah, so within the DJI Go Fly app, you can actually just start the LiDAR itself and then pretty much go in there. You do have to do the manual calibration, so you'll have to, fly the aircraft forward and backwards about 3 times at a high speed in order to calibrate it. Then you can continue on to scanning what you like and then adjusting the angle of the LiDAR, the L1 sensor. And then once you've completed that, just keep in mind that 100 seconds of you have to calibrate every 100 seconds. So you just have to keep in mind when you're doing the manual flight in that terms.
Fantastic. Well, actually, what you said there, Van, really neatly ties into the final question we have here, which is, can you go over the L1 IMU calibration requirements again, i.e. a line in turn sufficient for IMU recalibration on lines that are more than 100 or less than 100 seconds in length, or do you have to limit each flight to less than 100 seconds? So basically, Van just answered that. Yeah, you can fly a mission as long as the M300 battery will let you fly for sort of around that. What was it, 35 to 40 minutes generally. The main limitation there with the IMU and calibration is that it needs to be calibrated every 100 seconds of flight. So if you're flying at 10 meters per second, it requires a little bit of thought, I guess. If you're flying at 10 meters per second, then if you have more than 1 kilometer long flight lines, you're going to need to do a calibration before you get to the end of the line. If it's less than a kilometer, just turning the corner at the end is going to be enough to calibrate the IMU, and that's something that is automatically organized in DJI Pilot. The one area where you could get caught out and that you have to be careful about is if you're planning on flying a lot slower, then the line length that you can fly without having to recalibrate also gets smaller. So if you're flying at 5 meters per second, then you need to calibrate every 500 meters.
I think there's one. Did you see the question about UGCS, Tom?
Okay.
I think we missed. Is it practical to do the planning for L1 flights in UGCS?
Yeah, I see that. Okay, that would probably be a Van question.
Yeah, sorry about that. I had myself muted. We personally haven't tested the L1 with the UGCS, so I can't really speak to that at the moment. However, in the past, we have used UGCS for mission planning for our other LiDAR system with success. So yeah, as we continue testing the system, we'll certainly be looking into UGCS. But as it stands, the flight planning software from DJI Pilot, it's working very well. The only thing that I can think of that wouldn't work with UGCS is because it doesn't have the automatic calibration functionality that the Pilot has. So perhaps they might be able to add that in the future. But in the meantime, I would just use the Pilot app. That would be your best option.
Fantastic. I just realized we missed one other question up the top there. For the L1 or the P1, how to get sub 1 centimeter accuracy. Now with the L1, it's not going to be possible to get sub 1 centimeter accuracy. The main limitation there is just because it's because the L1 calculates point coordinates for the point cloud based off a GNSS, an IMU, and LiDAR sensor all combined together. You have cascading errors in it, or I guess systematic compiling errors in each of those elements, which make up that 5 centimeter accuracy that we talked about. So just flying lower, while that's going to reduce the amount of noise in your model and is going to increase the point density, you're going to get a much denser point cloud. It's not going to make it like 1 centimeter accurate or much more accurate. Whereas the P1, you can theoretically get sub 1 centimeter accuracy without too much difficulty. As we mentioned, at 120 centimeters, we had a GSD of 1.8 centimeters. So just by straight calculation, if you flew at 40 or 50 meters above the ground, you would be getting down around a GSD of 1 centimeter. Now, obviously, a GSD of 1 centimeter doesn't mean your entire model is going to be accurate to 1 centimeter. That just means the resolution is 1 centimeter. To get actual 1 centimeter accuracy, you're going to have to do some fairly careful control planning, installation, marking up, and survey. To get sub 1 centimeter accuracy, I'd say that you probably want to be either doing a static GNSS GCP network, or you want to be doing some kind of least squares adjustment with total station based Travis network. So there you're getting into, I guess, if you're a survey consultant, that's pretty well within well within sort of the expected bounds of what you could do. But there certainly is more challenge to getting a super high level of accuracy with that. The P1 can achieve that, but you're going to be relying on getting using a super accurate GCP network to constrain your bundle adjustment. You won't just get that by flying lower and relying on the RTK positions. So we've got one more question has just popped in. Can we do PPK with the L1 and Terra, and does it improve accuracy? That's a great question. From what I believe, the DJI Terra does use PPK, or it does calculate PPK solutions using the DRTK raw base file, and yeah, the P1 I guess conversely does use the actual RTK position. So you've got to consider that when you're thinking about the way you plan your survey in the field. So the one other thing to mention with PPK is that you can also use other file type or other GNSS antenna types to get RINEX data to process in DJI Terra. It's not a straight drag and drop functionality. You do have to change one or two file names around, but again, I'm sure that's something that DJI will be working on making even more user-friendly in future. So one more question. They keep rolling in. Best type of targets to use for GCPs. That really depends on your application and what kind of payload you're using. So if you're doing a LiDAR survey, you want to be using GCPs that are going to be able to be viewed by intensity values. So what that means is you want to have really high contrast or contrasting reflectivity targets. A typical checkerboard target will suffice, but you'd really be recommended to get a large size target because you're dealing with a lot less. You're dealing with a comparatively low point density to, say, a photogrammetry model. You definitely do need to have a larger target to be using. One other consideration is when you're, if you're selecting the type of GCP you're going to use, anything that's going to be, I guess, able to be differentiated from the surrounding ground in terms of elevation could also be a good option. There are plenty of options out there, retail options out there today. So that's all the questions that I see here. Were there any other final closing comments that Russell or Van you had?
No, not from me. Just wanted to thank everybody for their attendance. Some great questions. I definitely learned something from you guys, as always. That's it from me, Van. Yeah,
I wanted to say thank you for everybody for taking their time out this morning to join our webinar. And yeah, we're always here. Our email is on the bottom screen here. You can always feel free to reach out to us with any further questions or concerns. And we'll be posting this webinar on our YouTube channel and our social media, so you can rewatch it from there.
Fantastic. Well, thanks very much, guys. And as always, yeah, you've got our contact details there. If you have any inquiries about rental, service, or sales, please get in touch with us. We'll be glad to connect with you.